Up till now, we are able to find out the shear stress and the angle of twist in the case of solid shaft and the hollow shaft if it is subjected to constant load. And we have solved the problem for single shaft and the multiple shaft with the number of torque applied as well as composite shaft also. Now in this video we are going to discuss those cases in which either the torque itself is variable over the from A to B, the torque is uniformly distributed as equal to T. In that case we are interested here where will be the maximum shear stress. Naturally at this point we have torque equal to 0 and the torque intensity will go on increasing. So we have T plus T plus T like this one. So you have to add this value of T over the length L. In that case the maximum torque will possible at the point A, and therefore our set our axis at point B and we'll measure the distance from B to A will be positive distance. In that case we'll find here the maximum value of the shear stress will be at point A and the minimum value that equal to 0 at point B. But as the angle of twist is considered, angle of twist is 0 at point A because of the fixed support, and we have to calculate here the angle of twist at point B will be the maximum value. This is the one case that we are interested, which one is a variable torque. Second category of the problem in which the cross section area itself is variable. It has a larger area at the fixed end and the area is gone decreasing. And we apply a constant torque equal to T at the free end, and we are interested to know again where is the maximum value of the shear stress. And at point B we are interested to know what is the angle of twist. And the third case is that a material property, that is the value of G itself is variable. Then how we going to solve the problem? So in this video we are going to consider the either we have variable cross section or the variable torque or variable material property. The method of integration will work when we have the change in the cross section area, when we have the change in the torque over the entire length. Then the internal torque Ts is varies continuously, or the area will vary continuously, or the material property Gx may be vary. So let's say here we have T is a function of x, is the internal torque at any position x, at which one is variable and can be expressed in terms of x. Or in the case of the non-uniform cross section, we can claim here the polar moment of inertia is variable and is a function of x. At the same time, if the material property also variable, then we'll say the modulus of gt is a function of x. And if all these are the function of x, since we are knowing here the value of theta is given as T multiplied by L divided by J divided by G. The total twist angle can be computed by method of integration. We have to just integrate here Tx as same as this term, then J is replaced as Jx and G is replaced as Gx. And L will be replaced as dx. So we'll consider here one finite element at distance equal to x. We'll calculate here elementary value of d theta and we'll integrate that value from 0 to L. In that case we are able to find out what is the total value of angle of twist. Yeah, as far as this numerical is considered, we will find here that the value of the Jx, that is the polar moment of inertia, is not a function of x because this one is uniform diameter shaft and therefore the polar moment of inertia remain constant, as well as the value of G, that is a material property, also remain constant. So out of Tx, Gx and Jx, all the values will not be the function of x. At a time one will be the function of x. So you have to put up here Tx, Gx will be same as G, Jx will be same as equal to J, and we can calculate here the value of theta. As far as the second case is considered, where we have variable cross section and a constant torque, in that case the value of Tx is remain constant over the entire section from A to B. Value of G is also remain constant from A to B, but the polar moment of inertia is variable. Polar moment of inertia for a solid shaft is given as pi by 32 d to the power 4. So we'll consider here one diameter at distance equal to x. We'll develop a relation between the diameter at any distance x between d1 and d2 and we'll integrate it. So in that case the value of Tx will be same as equal to T, G will be same as equal to G and J will be a function of x. So this one is our approach in the present video when we are going to cover the variable torque, variable cross section or the variable material property. So we'll consider here a prismatic bar AB of length equal to L and is a solid circular cross section of diameter equal to D, is loaded by a distributed torque T of a constant intensity per unit distance. And in this situation we are interested to know what is the value of maximum shear stress And what is the value of theta b? That is the angle of twist at the free end. So when you have to solve this problem, then you have to use the method of integration, and you have to set our axis at point B. Consider here one section at a distance equal to x from B of thickness equal to dx. At that point we'll calculate what is the total torque, which one is the sum of the torque over the distance equal to x. Once we know the total torque for that element, we'll calculate the value of d theta, angle of twist, for the small section equal to dx, and then finally by method of integration we can able to find out the value of theta b. As far as tau max is considered, you have to identify where we have maximum value of the torque. Now, so let's say here T represents the intensity of a distributed torque, D represents the diameter of a solid shaft, and G represent here the shear modulus of elasticity. Out of that, the diameter D and the value of G is remain constant, will not change with respect to x. We'll consider here a section at a distance equal to x from A and B, where we have set up our axis x. At B we have x equal to 0, at A we have x equal to L, and we'll consider here a very small element of length equal to dx. And at this section here we'll consider the tx, which represents the internal torque at position equal to x. So we'll cut the figure at distance equal to x here, and we'll show the FBD here. And at this point we have tx represents here the internal torque at position equal to x. Then we can calculate the value of tx by the method of integration. The value of the torque intensity is remain constant, so at this point you can calculate the value of tx, that is the torque at position x, by method of integration. It's an integration of t dx, and we have taken the shaft length equal to x, 0 to x. So at any distance x we have the torque equal to tx is equal to t. Integral of dx is same as equal to x, upper limit is equal to x, so we have x minus 0, so it is t multiplied by x. It means that the torque is uniformly varying from B to A. At B the torque will be equal to 0, and at A the torque will be maximum. So at free end, that is at point B, we have value of x is equal to 0, so torque acting at point B will be equal to 0. Whereas at the fixed end A, we have x is equal to L. In that case the torque acting at point A will be equal to T multiplied by L. Naturally this value is the maximum value of the torque, and if the torque is maximum and the shaft is solid and the diameter remain constant and G is also constant, then the maximum value of the shear stress will occur at point A. A is given by T max is equal to pi by 16 into d cube multiplied by maximum shear stress, and the value of T max is same as equal to T multiplied by L. So from this equation we can calculate the value of maximum shear. So we have value of maximum shear, which one is given as tau maximum is equal to 16 will be multiplied here, so we have 16 times T multiplied by length L divided by pi into d cube. So one value of the shear we have to find out. Next value we have to find out the value of theta b. Theta b again we can find out for this small element, that is the d theta we'll find out first, and then we'll integrate again from x equal to 0 to x equal to L. So angle of twist at the given element will be equal to d theta, which is same as equal to torque. So we have to write down external torque equal to tx multiplied by the length of the given section equal to dx. It's a t into L divided by j, that is the polar moment of inertia multiplied by modulus of rigidity. And to find out here total angle of twist, we'll just integrate d theta. So let's substitute here first. We have tx will be replaced as t into x, so we have d theta equal to t multiplied by x multiplied by dx. J will keep as it is, that is a constant value, and the g will be same as it is, that is a constant value. So the angle of twist will be obtained by method of integration, and you have to integrate here d theta from 0 to L. Now t is a constant value, j is a constant value, and g is a constant value, so that quantity will take it outside. So we have t divided by polar moment of inertia multiplied by modulus of gt into integral x dx from limit 0 to L. This time we have integral of x is x square by 2, that will be L square by 2. So the angle of twist will be equal to T multiplied by L square and divided by 2 times of polar moment of inertia G divided by the modulus of Ut equal to G. And then again you can substitute for J and we can simplify the equation in terms of pi d. Final substitution we can do as pi by 32 d to the power 4, and we can develop here another expression for angle of twist. In the last part we have taken the value of Tx is remain constant over the entire length of the shaft from A to B. This time we will consider here that the Tx is variable, its value is 0 at the A and B and it is go on increasing, and the maximum value will be at A. At A we have the Tx value will be same as equal to Ta, and at point B the value of Tx will be equal to 0. So this is a difference here, it's a uniformly varying torque. Or otherwise, to illustrate here how exactly it is variable, we can use this diagram. This one is fixed end equal to A, this one is free end equal to B. At point B here we have value of Tx equal to 0. At this point here the value of the Tx will be same as equal to Ta. At any distance x here we have value is equal to Tx. So axis system will set at point B and will mark a distance equal to x. At this point here we have corresponding torque will be equal to T, which is a function of x, and we'll consider here a very small element of thickness, that is the length equal to dx, and we assume here the value of Tx over this section is remain constant. That is our assumption. So actually you have to imagine this one is a very small thickness, so that you can get the average value of the torque over the section is almost same value. In this numerical also we are interested to know what is the value of maximum shear. Naturally the maximum shear will be at A because all these value will be added and the maximum torque will be at point A. So we are interested to know what is the maximum value of the shear stress. Then at point A we have fixed end, so value of theta A will be equal to 0. At free end we have theta you have to calculate, that is the theta B you have to calculate. Again this problem has to be solved by method of integration. So we'll consider here one element of length equal to dx and we can compute the value of Tx. So we'll develop here the relation between Tx and Ta. Now you can observe this triangle here, which one is a larger triangle, has a height equal to Ta, base equal to L. This triangle here, which one is a smaller triangle, has a height equal to Tx and the base equal to x. So we can say here we have Ta divided by L is same as equal to Tx divided by the distance equal to x. So we can calculate here the torque intensity of a distributed load. So using the similar triangle property we can calculate here the intensity of a distributed torque, that is the value of Tx we can calculate. In this case we have torque intensity at point A will be Ta divided by length L, that is the length of the shaft, multiplied by distance x. So we have developed this equation and the rest procedure will remain same. Once we develop the expression for intensity of a distributed load, that is Tx, we are able to calculate what is the value of capital Tx, which one is internal torque at position equal to x, which one is nothing but the sum of all the torque from the given element up to point B. So this value of Tx we can obtain by method of integration. So we have Tx equal to integral of Tx into dx from 0 to x. So this is generalized expression we can develop for the internal torque at position equal to x. So let's substitute here. We have integral Tx can be replaced as the torque Ta multiplied by x divided by L multiplied by dx, and we have limit is from 0 to x. In this case the value of Ta and L is a constant value that can be taken outside. So we have Ta divided by L. Integral of x is x square by 2. So we have x square divided by 2. The lower limit is 0, that is meaningless. So at any distance we have torque is equal to Ta into x square divided by 2 times of L. Using this, we can calculate the torque at B and torque at A. So at free end, we have x is equal to 0. So if I put here x is equal to 0, I will get the value of Tx will be equal to 0. At fixed end, that is at point A, I have to put the value of x equal to L. In that case, I will get the torque Ta at end A. You have to just substitute here x equal to L. In that case, it will be L square by L, that equal to L. So this value is same as Ta multiplied by L divided by 2. We know the value of the torque at A, which is Ta multiplied by L divided by 2, and this value is a maximum value. And using the maximum value, we can calculate the value of tau max. So for remaining portion, I will use the value of Tx equal to Ta into x square by 2L, and the maximum torque at the fixed end A is equal to Ta multiplied by L divided by 2. Just substitute here x equal to L. So we'll continue on the next slide. So at any distance x, we have to internal torque Tx equal to Ta into x square by 2L. At fixed end, we have maximum torque equal to Ta into L by 2, and we have maximum torque equation is given as T maximum equal to pi divided by 16 into diameter cube multiplied by maximum shear stress. So we have T maximum is same as Ta multiplied by L divided by 2 is equal to pi divided by 16 into d cube into tau max. So the maximum shear at end A is given as, so these two will be cancelled, and with 16 is 8 is left, 8 is multiplied here, so we have 8 times Ta multiplied by L divided by pi multiplied by d cube. Next job is to calculate the value of theta b. To calculate the value of theta b, again we have to consider here one element of length equal to dx. So that element we can show somewhere here of small length equal to dx. Over this section we can calculate the value of d theta as TL by Jg. So we have to consider here the internal torque equal to Tx. Length of the element is dx, so L is replaced by dx divided by J divided by G. Now the internal torque Tx we are knowing is given as Ta into x square by 2L. So we have d theta equal to Ta multiplied by x square divided by 2 times of L and further divided by J and G, and is multiplied by dx. So this one is the equation we have to use to calculate the total angle of twist at end B. At theta at A will be equal to 0. So again you have to integrate this equation over the entire length from 0 to L, and we can calculate the value of theta B. Out of that, Ta divided by 2 LJG is a constant value, only variable is x square. So we have theta equal to Ta divided by 2 times of L into J into G, and we have integral of x square dx, and we have limit is from 0 to L. So we have theta equal to Ta divided by 2 times of L multiplied by J multiplied by G. Integral of x square is x cube by 3. So that will generate L cube divided by 3. So one of the L will be get cancelled. In the numerator we have left here with L square. So we have theta equal to Ta. One of the L is cancelled, so we have L square divided by 2 into 3, that will be 6, and the value of J is equal to pi divided by 32 will shift in numerator into d to the power 4 multiplied by G. So if I divided by 2, I will get this term equal to 3 and this term equal to 16. So finally we are getting here theta equal to 16 times Ta multiplied by L square divided by 3 times of pi into d to the power 4 into G. That is the modulus of rigidity. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.